Hi. So before the break, we saw how to solve circuits with only one capacitor, discharging or charging. But now we look at more complex situations. For example, if you have several capacitors. Um, Now the simplest case we can think of is this one here, where let's say you have two capacitors in, let's say in series, connected to just one battery. Okay, now what happens? Let's say you have a switch here, and you close the switch at t equals 0. Again, let's assume that we start with two capacitors that are initially uncharged. So when you close the switch, they have no charge on their place, and we close the switch. What happens? The battery here will push positive charges away from the positive terminal here. Positive charges will flow like this here and start to accumulate here. So you end up with a charge plus Q on this plate. Now at any time on a capacitor, the charges on the two plates are equal apart from their sign. So if you have plus Q here, you have minus Q here. Now comes a key point. If you focus on this part of the circuit, let's say I circle here, I go inside the capacitor here and inside here. In this section of the circuit, notice that this is not connected to anything else directly. So this section of the circuit here, there's no charge that can be added or removed from that section. So if you started with the capacitor uncharged, there was no net charge at the beginning. If you end up with minus Q here, you must necessarily have a plus Q here, so that the total charge in this circle section is equal to 0, as it was at the beginning. So that's the key point. If you start with capacitors that are initially uncharged and they're connected in series, they will have the same charges on their positive plate. If you have plus Q here, you have also plus Q on that one. Okay, that's important. And therefore, because you have plus Q here, you have necessarily minus Q on that plate here. Okay, so that's very important, a key point. Capacitors in series have the same charge. I'm talking about charge on their positive plates, right? So if you have plus Q here, you have plus Q on that one also. Strictly speaking, this is not a general rule that applies all the time. It applies to cases where you have capacitors that were initially uncharged. But that's the cases we're going to look at in those circuits. So a capacitor in series have the same charge, okay? Obviously, they have different voltages. If you look at the voltage across C1 and across C2, there's no reason they should be the same, except if C1 and C2 were equal, if they had the same capacitance, because they have the same Q and if they had the same capacitance, they would have the same voltages. But if C1 and C2 are different, there's no reason the voltages would be different because they have the same charge, therefore different voltages. But what is true, what we can say that will necessarily be true is that if you look at the circuit, if you do the loop rule, the voltage between this point and this point is equal to DMF. Is equal to E, the EMF of the battery here. So between here and here, if you have a 12-volt battery here, the voltage between here and here is 12 volts. But that voltage must be equal to the sum of the voltage across C1 and the voltage across C2 because they're in series. Okay, so that's an important relationship here for this circuit. Okay, again, this is true because they're in series. Okay, now what we do, our goal is to replace this circuit by an equivalent circuit. The goal is what? Is to be able to say what can we replace if we want to replace those two capacitors here by an equivalent capacitance. What would be the value of the equivalent capacitance in terms of C1 and C2? That's our goal. So first I redraw the circuit here, replacing C1 and C2 by an equivalent capacitor with C equivalent, which is unknown. This capacitor here will have a charge plus Q and minus Q, because here you have plus Q and minus Q here. So you have plus Q and minus Q here. Our goal is, what's the relationship between C equivalent and C1 and C2? Okay, so that will tell us how to combine capacitors in series if we can find this relationship. So what do we notice? In this circuit here, obviously the voltage across the capacitor, the equivalent capacitor is E, the EMF, and for any capacitor, if you know the voltage across the capacitor and the charge on the capacitor, you have this equation here relating the voltage and the charge. Voltage across the capacitor is equal to charge divided by the equivalent by the capacitance. So for this circuit here, we know this must be true. Okay. What about this circuit here? Well, again, this circuit should be equivalent to that one here. So the EMF here is the same as the EMF here. In this circuit, we know that the EMF here is equal to delta VC1 plus delta VC2. So we'll get an equation, which is this. Okay, so this is what we got from the equivalent circuit. Oops. Okay, that's from the equivalent circuit. Now, for the original circuit, remember we had E was delta VC1 plus delta VC2. Now we can write that as this in this form. Delta VC1 is just Q on the first capacitor divided by C1, and delta VC2 is Q2 over C2. Okay, so this is this. But remember that because they're in series, Q1 and Q2 are the same. The two capacitors have the same charge. So this equation, we can write this form here. Okay, so this is the value of the EMF in the original circuit, and this is the value of the EMF in the equivalent circuit. Those two must be equal. So you set that equal to that, and then you see that the Q, you can cancel out the Q, and you end up with 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And that's it. That gives us the equation relating the equivalent capacitance in terms of C1 and C2. Okay, all I used was the fact that the EMF was the same in both circuits. So that's an important equation. We're going to summarize that in a second. So just to summarize, in series, equivalent capacitance are given by this equation, which is the equation you're used to see for equivalent resistors in parallel, but here it applies to capacitors in series. In series, the charges on two capacitors in series are equal to one another, and they're equal also to the charge on the equivalent capacitance. So if you replace C1 and C2 in series by C equivalent, they all have the same charge. C equivalent, C1, C2 all have the same charge. And the voltage across the equivalent capacitor, because it comes from two capacitors in series, is equal to delta V1 plus delta V2. Okay, so those are the three principles that we use for capacitors in series. Now, in parallel, I connect the battery here to two capacitors in parallel, C1 and C2. This time, the battery here is pushing charges this way. Let's say I'm pushing a charge Q. So Q is flowing out of the battery here. Q goes like this here, moves down here, and then it will split. Some of it will go here, part of it will go there. Now, there's no reason why it should split equally. Actually, if C1 and C2 are different, the charges, when the Q here, when it will split in a way that will not be equal. So you end up with a charge Q1 here and a charge Q2 here, and Q1 and Q2 are not equal. But what you can say is that the total charge moved by the battery here, capital Q, the total charge that flowed out of the battery, Q, is equal to the sum of the charge on the two capacitors. Okay? So this is very different from when we were in series. Now the total charge flowing out of the battery is equal to the sum of the charges on the two capacitors. Okay. Now what we do next? Well, as we did before. Before we do that, so let's just summarize what we just mentioned. Capacitors in parallel, the voltages are equal. Well, that you know. For any two elements in parallel, the voltages are the same. But in general, the charges are different. Okay. And the relationship is that the charge that flowed out of the battery is equal to Q1 plus Q2. Now, the charge on the first capacitor is equal to C1 times the voltage across the first capacitor. But the voltage across the first capacitor is just E, right? And the voltage across the second capacitor is also E, the EMF. So we have an equation for Q1 and Q2 in terms of C1, C2, and the EMF. So those two here, I can plug that in that equation, and I get the total charge that flowed out of the battery is equal to C1 plus C2 times the EMF. Okay, this equation tells us how much charge flowed out of the battery in terms of the two capacitance and the EMF. Now, what do we do next? As before, we replace our circuit by an equivalent circuit. So in this circuit here, you have the equivalent capacitance here that replaces our two capacitors in parallel now. And we have a charge, capital Q, that is flowing out of the battery here. Now, clearly, in this circuit here, the voltage here is E, and the charge accumulating here is Q, right, on this plate here. So you have that plus Q here and minus Q there. So you have this equation. The charge here, Q, is equal to C equivalent times E. Okay? But remember, In the original circuit, the total charge that flowed out of the battery is C1 plus C2 times E. So these two equations must be equal because they both represent the total charge that flowed out of the battery. So you set that equal to that, you cancel out the EMF, and you get this equation. In parallel, the equivalent capacitance here that replaces two capacitors in parallel is equal to C1 plus C2, okay, which is the equation you're used to see for resistors in series. And the total charge that flowed the total charge that accumulates here on the equivalent capacitance is equal to the sum of the charges on the two capacitors in parallel. And the voltages are the same because they're in parallel. So those are the three key rules for capacitors in parallel. C equivalent is equal to C1 plus C2. The charge on the equivalent capacitor is equal to the sum of the charges on the two capacitors in parallel, and the voltages are all the same. Okay. So, just to summarize, let's say you have a discharging RC circuit. Remember, just to remind you of the basic laws, you have this setup here, you have a switch that we close at equals 0. We have a capacitor here that has initial charge Qi, Q initial, let's say on one side or on the other side here. So you have a charge here, let's say Q initial here. Okay, we saw that for this circuit, we had those equations. Q on the positive plate as a function of time is given by Q initial times this exponential. And we can replace RC by tau. We call that tau. Now, the current in a discharging circuit was given by minus the derivative of QC with respect to time. So you just differentiate that with respect to time multiplied by minus 1. That gives you the current. Once you have the current, you can find the voltage across the resistor is R times I. And once you have the charge on the capacitor, on the positive plate, you can find the voltage across the capacitor is QC over the capacitance. This is what we saw before the break. Now, these equations you can only apply to this circuit. So you can only apply those equations to one capacitor and one resistor connected together. If you have several capacitors and resistors combined together, you must connected together, you must combine them into this circuit. You must combine everything down to one single equivalent capacitance, one single equivalent resistor, before you can apply any of those equations. Those equations apply only to the equivalent circuit with one capacitor and one resistor. So if you have several capacitors and resistors, you must combine them, and then once you have the equivalent circuit, you can apply those equations. Okay, we see examples of that in class, in the practice problems. Now, for charging RC circuits, what were the rules? Again, the equations we saw for charging RC circuits were only valid for one capacitance and one capacitor and one resistor and one battery. So if you have this circuit here, then in that case, the charge on the positive plate of the capacitor was given by this equation here. Then tau is always given by R times C. Then the current is given by the derivative of QC. And notice here there's no minus sign, it's positive. This is when you're charging the RC circuit because of the charge on the positive plate of the capacitor is increasing in time. We have a positive sign here. So I of t is just a derivative of this expression here. And again, once you have I of t, you can find delta VR. Once you have QC of t, you can find delta VC. These equations apply only to this circuit here with one resistor, one capacitor, and one battery all connected in series. If you have a circuit with several capacitors, several resistors, you must combine them into equivalent values and one single equivalent capacitor, one single equivalent resistor before you can apply any of those equations. Okay, so we'll see how to apply those principles in our practice problems in class. Thank you.